Section 20.4 Electronic Spectra of Complexes. Subsection D. The energies of the terms. Weak and strong field limits. We'll put a transition metal ion in a very weak versus a very strong octahedral field and look at the electronic transition energy between different terms. So first, let's look at the weak field limit. In a very weak octahedral field, delta O is close to 0. We can neglect the ligand field stabilization energy. We can assume the 5 different d orbitals have very similar energy. In this case, the transition metal center may be considered as a free ion. And then we can just look at the atomic terms and the energy expressions of these atomic terms and determine the transition energy. Rocca proposed these 5 energy expressions for the 5 atomic terms of the D2 electron configuration. When we put 2 electrons in the 5 d orbitals, the first electron has 10 options, the second electron has 9 options. And because electrons are indistinguishable, there are 10 times 9 over 2 factorial microstates. That's 45 microstates. And we can group these 45 microstates into 5 atomic terms, S, P, D, F, G, with a spin multiplicity 1, 3, 1, 3, 1. So they are listed here. Rocca proposed these energy expressions in terms of 3 parameters, A, B, and C. A is just the average electron-electron repulsion. And then B tells us the spatial distribution between these 2 d electrons. For example, if you have one electron in the dxy orbital, the other electron in the dz squared orbital, the repulsion is smaller than when you have 2 electrons, one in the dxy orbital and the other in dx squared minus y squared orbital. This is because the dxy orbital and the dx squared minus y squared orbital are on the same plane. If you look at the 4 lobes of dxy and the 4 lobes of dx squared minus y squared, they are really close to each other. And that means there's going to be stronger repulsion between these 2 electrons. And that's the reason why this 3p atomic term has higher energy than 3f by 15b. So this 15b is actually the energy difference between 2 scenarios. The first scenario, you have dxy and dx squared minus y squared, stronger repulsion. The second scenario, you have dxy and dz squared. In this case, you have less repulsion. The difference is 15b. B is a Rocca parameter for 3D transition metal elements. B is between 600 wave numbers and 1200 wave numbers. Now let's look at C. So first you need to determine the ground term and its spin multiplicity. And then C only appears in the atomic terms with a different spin multiplicity from the ground term. So that's why in here, 3p, there's no C. Because 3p has the same spin multiplicity as 3f. So you have 2c here, 2c here, 7c here for a different spin multiplicity. Okay, again, if you just have a very weak octahedral field, let's say if the ligand is aldehydo, bromido, all right, and then you can use these equations to estimate the energy difference between 3p and 3f. So this is the ground term, and then this is the excited state with the same spin multiplicity. And you can say, well, the electronic transition energy is roughly 15B. Alright, if you know the value of B, let's say B is 1000 wave numbers, and then the transition energy is 15,000 wave numbers. Alright? It's unlikely to observe the 3F to 1D transition or to 1G or to 1S because these transitions are spin forbidden transitions. The spin multiplicity changes from 3 to 1. That means you have to flip the spin of an electron, and that's spin forbidden. Now let's look at the strong field limit in a very strong octahedral field with a very large delta O. Then the splitting of the atomic terms must be considered. This is because now if you put an electron in the dx squared minus y squared orbital versus electron in the dxy orbital, there's a huge difference. If you have a strong field ligand such as carbonyl, cyanide, delta O can be as large as 30,000 wave numbers, even for 3D transition metal center. In that case, this 3F splits into 3 terms in the octahedral field. Okay? And the 3P will be maintained as only one term, but there's going to be energy shift as well. So we'll look at these 2 cases a bit later. For now, let's look at the simplest D1 electron configuration. In this D1 electron configuration, there's only one electron. This electron can occupy one of the 5 d orbitals, and this electron can be alpha spin or beta spin. Therefore, there are 5 times 2 microstates, 10 microstates. And we can group this 10 microstates together to get the atomic term. It's 2D. 2 is the spin multiplicity. D means L equals 2. And why is that? Well, since you have only one electron, then the sum of M sub L is equal to the value of M sub L of this single electron. That's -2, -1, 0, 1, 2. Therefore, the uppercase L for this atomic term is 2. And then you have S, P, D, F corresponding to L equals 0, 1, 2, 3. So that's why it's 2D. Now over here on the left hand side, you have 0 ligand field strengths. There's only one atomic term. There's no electronic transition because you have only one term. And then it splits into 2 terms in an octahedral environment. So over here, you have this electron in the dxy, dyz, or dzx orbital. Here, you have the electron in the dx squared minus y squared or dg squared orbital. So there are 2 terms in the strong ligand field. The difference is delta O. It can be as large as 30,000 wave numbers when you have a strong field ligand. Well, when you have 6 of them. And you will be able to observe an electronic transition for a D1 transition metal complex with an octahedral environment. And you measure this transition energy, that's equivalent to delta O. And delta O is the crystal field splitting parameter. So this is how we determine delta O experimentally. Well, somehow you just need to get a D1 transition metal center. For example, scandium 2+, titanium 3+, etc. And then you look at the UV-vis spectrum of this D1 transition metal complex, and that transition energy is equivalent to delta O. Now let's look at the this letter E and this letter T. They are both upper cases. So why not lower cases? Well, when we are looking at electrons individually, so one electron, we use lowercase t, lowercase e. When we are looking at the atomic terms in the free ion case, or the splitting of atomic term in an octahedral environment, we still view this as terms of multiple electrons. We are grouping those electrons together, despite the fact that there's only one electron here. So you can view this as a group of one electron. Alright, so you can view this electron as a single electron, or you can view this as one group of an electron. So this is just for consistency. When we are looking at terms, we use uppercase letter E and T. Now let's look at D2 electron configuration. Now we have a group of 2 electrons. And there are 5 atomic terms, S, P, D, F, G, with spin multiplicity 13131. Let's look at the ground term. It's 3F. And then we can observe electronic transition from 3F to 3P, but not to any other singlet spin state. So just 3F to 3P. 3F to 1s is forbidden. 3F to 1d is forbidden. 3F to 1g is also forbidden. So now let's look at this energy diagram. On the left hand side, you have the free transition metal ion with a D2 electron configuration. Again, let's just look at the ground term and this 3p term with the same spin multiplicity. Okay, and we don't care about 1s, 1d, or 1g. Again, because there's no transition between a triplet spin state to a singlet spin state. The difference between these two is 15b. It comes from Raka's energy expression. So you have A minus AB, A plus 7b. The difference is 15b. And why is that? It's because of the difference in the spatial distribution of the electrons. So again, over here you have 2 electrons in 2 different d orbitals with the same spin, and these 2 d orbitals are not in the same plane. Over here, you still have 2 electrons with the same spin, but these 2 electrons are occupying 2 d orbitals in the same plane. For example, dxy and dx squared minus y squared. These 2 d orbitals are both in the xy plane. Therefore, the electron-electron repulsion is stronger here. How much stronger than this case? 15b. And now we start to increase the ligand field strength. We include this delta O in our energy expression. Alright, so we're going to look at 1, 2, 3 cases. This 3F atomic term splits into 1, 2, 3 terms because in this 3F term we have 2 electrons, both of them, in the dxy, dyz, or dzx orbital. Over here, we can have 1 electron in the dxy, dyz, or dzx orbital. The other in the dx squared minus y squared or dz squared orbital. Over here, both electrons are in the eg orbitals. So that means 1 electron is in the dz squared orbital, the other dx squared minus y squared orbital. So in this case, we have both electrons in the eg orbitals, and we have higher energy due to this ligand field. And now let's look at these three pink lines. As the ligand field strength increases, the splitting gets larger and larger. Well, this is because, again, over here, we have these two electrons below the barycenter. Here, one electron above the barycenter, one electron below the barycenter. Over here, two electrons are both above the barycenter. The Eg orbitals are 0.6 delta O above the barycenter. The T2G orbitals are 0.4 delta O below the barycenter. So over here, this term is 0.8 delta O below the original point. Okay? And over here, this energy level, you have positive 0.6, negative 0.4. So together, you have positive 0.2 delta O above this point. And now finally here, Eg2, 2 electrons in the Eg orbitals. So you have 0.6 delta O times 2. So this is 1.2 delta O above here. Alright, again, 0.8 delta O below this, 0.2 delta O above this, 1.2 delta O above this. Alright. Now let's look at the blue line. So if you look at the blue line, it's 15B above 0 at the beginning when the ligand field is 0. Now when we include the ligand field strength, later I'll show you this 3p also correspond to this situation. One electron in a T2G orbital, the other in the Eg orbital. So over here, we still need to include this delta O. And remember, this is negative 0.4 delta O. This is positive 0.6 delta O. So together, it's 0.2 delta O. And then plus 15B. So this is 0.2 delta O plus 15B. And then we have 4 terms, okay, in the octahedral environment with 4 different energy expressions. Now, why is this 0, delta O, 2 delta O instead of negative 0.8, 0.2, and 1.2? Well, this is just for convenience. So on this side, we can choose a different zero reference. All right, so this zero reference is different from this zero reference. Arbitrarily, we just say, well, this negative 0.8 delta O becomes the zero reference, so it's 0. And this is just delta O above 0. This is 2 delta O above 0. This number is 15B plus delta O above 0. It's just for convenience. And then the transition energy is delta O, 2 delta O, delta O plus 15B. Alright, so if you have a D2 transition metal complex with 6 ligands in an octahedral environment, in the UV vis spectrum of this complex, we expect to see 3 peaks. They correspond to delta O plus 15B, and 2 delta O. Alright, so if you know the values of B and delta O, you can just make predictions of the UV vis spectrum of the D2 transition metal complex. Again, it's just delta O plus 15B, and 2 delta O. So supposedly over here, this is delta O plus 15B, right? And this is 15B. So supposedly, the difference between this 3T1G and this 3T2G is a constant 15B, right? So supposedly this blue line and this pink line should be parallel. However, well, obviously it's not parallel to each other. What's the reason? Well, in a free ion, B is larger. Okay, B is larger. B is the repulsion caused by putting 2 electrons in two d orbitals in the same plane. For example, dxy and dx squared minus y squared. And this B is larger when you have a free transition metal ion. It's smaller when this ion is surrounded by ligands. Why? Well, the 6 ligands may help disperse these 2 electrons and reduce this parameter B. So I want to tell you, this is 15B. This smaller gap is still 15B. It's just now you have a smaller B. Okay, over here you have a smaller b. Same 15b expression, but b becomes smaller here. So that's why this blue line and this pink line are not parallel to each other. Now again, when delta O is 0, that means the ligand field strength is 0. We are looking at essentially a free ion. The 3p atomic term lies 15b above the 3f term. Alright, in this case, we can still observe a electronic transition. Right? And the transition energy is 15b. And then if we put this transition metal center in an octahedral environment with 6 strong field ligands, well, on this end. And then we'll have to consider the crystal field splitting, delta O. The dxy, dyz, dx orbitals are triply degenerate. They have 0.4 delta O energy lower than the barycenter. Meanwhile, dz squared and dx squared minus y squared lie above the barycenter by 0.6 delta O. So we need to take that into account when delta O is large. Alright? And then let's look at the 3p term. The 3p term also include a situation, so this situation in which one electron is in one of the Eg orbitals. The other electron is in one of the T2G orbitals. So this is the electron configuration associated with this term. So this looks exactly the same as this, right? So shouldn't they have the same energy? Well, actually no. The reason is simple. Over here, again, you're looking at the 2 electrons occupying 2 different d orbitals that are not in the same plane. That means the repulsion is smaller. Over here, you have 2 electrons also occupying 2 different d orbitals, but these 2 d orbitals are in the same plane. Let me give you a few examples. Over here, this term has higher energy than this term because these 2 electrons can be in the dxy orbital and dx squared minus y squared orbital. So that's larger repulsion. These 2 electrons can be in the dxz orbital and dz squared orbital. And these 2 are both in the xz plane. These 2 electrons can also be in the dyz orbital and dz squared orbital. These 2 are also in the same plane. Now let's look at this situation. You can put one electron in the dz squared orbital, right? And then this electron is in the dxy orbital. These 2 d orbitals are not in the same plane. dxy and dz squared, they are not in the same plane. That's repulsion there. Also, you can put one electron in the dx squared minus y squared orbital. The other electron in the dyz orbital or dxz orbital. And still, they're not going to be in the same plane. Less electron repulsion here. More electron repulsion here. What's the difference? 15b. Unfortunately, this b changes. When you have a free ion, you have a larger b. When this ion is surrounded by ligands, you have smaller b. Because the ligands help disperse these two d electrons. So that's why this blue line and this pink line are not strictly parallel to each other. But still, I mean, the difference is 15b here, 15b here, 15b here, 15b here. It's just this 15b is smaller than this 15b. So again, I want you to look at this two bullet points and to picture the two d orbitals in the 3f term. Okay? And the two d orbitals in the 3p term. All right? So there's a difference here. Again, this T2G originates from 3f. You may put these two electrons in this 2d orbitals, or this two, or this two. Okay, and in each pair, you'll see the 2d orbitals are not in the same plane. Okay, they are perpendicular to each other. And that means less repulsion. Over here, this T1G comes from 3p. In this case, these two are in the same plane, these two are in the same plane, and also these two are in the same plane. There's a larger electron-electron repulsion. How much larger? 15b larger. All right? And then finally, I want to explain here. If you look at this, this is EG1, T2G1. This is also EG1, T2G1. But how come you have this term with this 2G label, this term with 1G label? So 1 and 2, that means, well, they are symmetric and anti-symmetric with respect to the rotation of the principal rotation axis. So how is that possible? All right, now let me explain this symmetry here. So why don't we just fix the orbital for this electron? Let's say this electron occupies the dxy orbital. All right, dxy. And then we can put the second electron either in the dz squared orbital with lower energy, or in the dx squared minus y squared orbital with higher energy. All right. And now if you look at the dz squared orbital, it's symmetric with respect to the rotation about the z-axis by 90 degrees. Right? It's a C4, rotation symmetry element. Now if you look at dx squared minus y squared, and then you rotate this 90 degrees about the z-axis, you will see the sign of the wave function changes. Alright, so if you just plot this dx squared minus y squared, you will see the lobes on the x-axis are positive. The lobes on the y-axis, the two lobes along the y direction, are negative. And then if you rotate this 90 degrees, the plus sign becomes negative sign. Negative sign becomes plus sign. So after the rotation, you're going to change the signs for the dx squared minus y squared orbital, but you will not change the sign of the lobes in the dz squared orbital. So that's why, although they have seemingly same electron configuration, one electron in the T2G orbital, one electron in the EG orbital, but they do have different symmetry, and it's reflected here. You have one here, and then you have two here. And one more thing, I was assuming this T2G electron is the dxy electron. All right. So if you do a C4 rotation, this dxy will also change sign. The four lobes of dxy will also change sign. All right. So now if you have dxy changing the sign, and then you have dx squared minus y squared changing the sign, together you do a multiplication. -1 times -1, you get +1. So when you have these two electrons, one in dxy, one in dx squared minus y squared, and then you look at the rotation about the C4 axis, the total wave function of the two electrons is symmetric. That's why you put 1 here. Now over here, you have dxy, which is anti-symmetric with respect to the C4 rotation. You have dz squared, which is symmetric with respect to the C4 rotation. So you have plus 1 times negative 1, you get negative 1. Negative 1, that means anti-symmetric with respect to the rotation about the C4 axis. That's why you put a 2 here. So that's why this is 3t1g, this is 3t2g. Okay, what about the g's? Well, all d orbitals are symmetric with respect to the inversion center. That's why you see g here. All right.